Welcome to the online training, Clock Domain Crossing Considerations. My name is Steve. This presentation consists of 4 main sections. In the first 2 sections, I will review what is metastability and what are synchronizer circuits. Next, I will go over the reporting and various features of the CDC Viewer and Timing Analyzer, which is found in the Intel Quartus Prime Pro software. I will then go over a simple design that crosses clock domains and explain the constraints necessary to mitigate any metastability problems. First, let's do a quick review of what is metastability. All registers in digital devices, such as FPGAs, have defined signal timer requirements that allow each register to correctly capture data at its inputs and produce an output signal. To ensure reliable operation, the input to a register must be stable for minimum time before the clock edge, called register setup time, and for minimum time after the clock edge, called the register hold time. When data is captured correctly, the register output is then available for a specified clocked out delay. If a data signal transition violates a register setup time or hold time requirements, the output of the register may go into a metastable state. In a metastable state, the register output hovers at a value between the high and low states for some period of time, which means the output transition to a defined high or low state is delayed beyond the specified clocked out. The time it takes for a signal to resolve to a known high or low state is unpredictable. This figure shows example metastable signals. The input signal transitions from a low state to a high state, while the clock signal transitions, violating a register setup time requirement. The data output signal example starts in the low state and goes metastable, hovering between the high and low states. The signal output A resolves to the input data's new logic 1 state, and output B returns to the data input's original logic 0 state. In both cases, the output transition to a defined 1 or 0 state is delayed beyond the register's specified clocked out. If the data output signal resolves to a valid state before the next register captures the data, then the metastable signal does not negatively impact the system operation and there is no design failure. Note that the designer must use proper design techniques to handle asynchronous signals or signals crossing clock domains. We'll talk more about this in a little bit. If the metastable signal does not resolve to a low or high state before it reaches the next design register, it could cause the system to fail. Failure can occur when the time it takes for a stable state of 1 or 0 exceeds the allotted time, which is the register's clocked out, plus any timing slack in the path from the register. When a metastable signal does not resolve in the allotted time, a logic failure can result if the destination logic observes inconsistent logic states. That is, different destination registers capture different values for the metastable signal. Imagine one register captures an output that resolves to the new data after the signal transition, while a second register captures an output that resolved to the data signal before the transition. The rest of the system would probably behave incorrectly because the logic values are inconsistent. Now, a quick review of synchronization circuits. When a signal transfers between circuitry in unrelated or asynchronous clock domains, it is necessary to synchronize this signal to the new clock domain before it can be used. The first register in the new clock domain acts as a synchronization register. To minimize the failures due to metastability in asynchronous signal transfers, circuit designers typically use a sequence of registers called a synchronization register chain or synchronizer in the destination clock domain to resynchronize the signal to the new clock domain. These registers allow additional time for potentially metastable signals to resolve to a known value before the signal is used in the rest of the design. The extra time reduces the probability that the signal will be metastable at the end of the chain. The timing slack available in the synchronizer register-to-register paths is the time available for a metastable signal to settle and is known as the available metastability settling time. Dual clock asynchronous FIFOs are popular to use to cross clock domains. The FIFO logic uses synchronizers to transmit control signals between the two clock domains. Then data is written and read with dual port memory. Intel offers a DC FIFO IP core for this operation, which includes various levels of latency and metastability protection for the control signals. A synchronization register chain or synchronizer is defined as a sequence of registers that meets the following requirements. The registers in the chain are all clocked by the same or phase-related clocks. The first register in the chain is driven from an unrelated clock domain or asynchronously. Each register fans out to only one register except the last register in the chain. The length of the synchronization register chain is the number of registers in the synchronizing clock domain that meet the above requirements. Figure shows an example synchronization chain of length 2, assuming the output signal feeds more than one register destination. Metastable signal must resolve in chain before output signal is captured by multi-design registers. Next, I will go over the CDC Viewer found in Timing Analyzer. The CDC Viewer is a reporting tool found in Timing Analyzer that allows you to quickly view in an easy-to-read grid the relationship between the clocks in your design. The boxes in the grid are color-coded so as to easily recognize passing, failing, unrelated, and cut paths. The grid in the Setup Transfers report can be configured to display clocks as either flat lists or in a hierarchy, where generated clocks are displayed as children of the clock they are derived from. The CDC Viewer allows the endpoint counts, worst-case slack, and total negative slack for each related clock. Right-click in each grid to generate reports and create SDC commands for the specific clock transfers. The available context menu options are shown in the slide. The reports support both plain text and HTML outputs. The legend in the CDC Viewer report shows the color coding associated with the grids and allows you to toggle data on and off depending on which bit of information you want to focus on. Clock Group section shows that the source and destination clocks of these transfers have been cut by means of the setClockGroups SDC command. The Fails Timing section indicates that one or more of the timing paths in the transfer do not meet their timing requirements. If the transfer is between unrelated clocks, the paths likely need to be synchronized by a synchronizer chain. Cut transfer means that all paths in this transfer have been cut by false paths. The result of this is that the paths are not considered during timing analysis. Inactive transfer indicates that one of the clocks involved in the transfer has been marked as an inactive clock with the setActiveClock SDC command. Such transfers are ignored by Timing Analyzer. Past this timing mean that all timing paths in this transfer that have not been cut meet their timing requirements. No domain crossing transfers. There are no paths crossing between the source and destination clock. At any point in CDC Viewer where you need to search for nodes or nets, you can use wildcards for your search. Live filtering immediately removes unmatched names as you enter your search criteria. The default report when CDC Viewer is launched from the task window is the setup analysis. You will always want to analyze hold, recovery, and removal values as well. You can run the commands listed on this slide to get a time report for hold, recovery, and removal analysis. Let's look at a simple design. The design that I made to illustrate clock domain crossing consists of 2 multipliers and 3 adders. I will only focus on the adder portion of the design. There are 2 clock domains for the 3 adders. I feed the results of one adder into a synchronizer circuit, and the result of the synchronizer circuit goes into the final adder. After running the CDC Viewer on the design, you can see that the setup analysis fails at the clock domain crossing for both the 2 adder clocks and the 2 multiplier clocks. Again, I'll only focus on the adder portion of the design. Part of what I need to do with my simple design is to add a synchronizer. I'll now go into more detail on the assignments and SDC commands needed to create a synchronizer. The software tools automatically detect synchronizer circuits, but we can also manually tell the tools about the synchronizer. The synchronizer identification force to face synchronous assignment tells the tools that it is a synchronizer chain if Reg2 has a clock that is asynchronous to the clock of the preceding register, which means that the tools will place the synchronizer registers as close together as possible. The tools will automatically detect a synchronizer, but the assignment is available if you want to be sure not to leave anything to chance. The synchronizer register chain assignment exists in the default settings with an assignment of 3. The example here is really to let you know that this assignment exists by default, and any synchronizer chain has a global default length of 3. The synchronizer register chain length is a local assignment attached to a specific node. This local assignment will override any default or non-default global assignment. The clock constraints demonstrate the 2 clock domains. The setFaultsPath SDC command tells Timing Analyzer and subsequently the fitter not to consider the paths between those 2 clock domains. The fitter can make the paths as long or short as it needs to. This can cause skew problems with the bus, given that one bit of a bus can be captured by the clock edge before another bit of the bus arrives for the same clock edge. The setMaxSkew SDC command is the constraint you need for such a situation, but the setFaultsPath negates a setMaxSkew constraint placed on a bus. Instead of using the setFaultsPath constraint, you could use the setClockGroups constraint. The setClockGroups constraint tells Timing Analyzer not to analyze paths between clock domains, and it does not negate a setMaxSkew constraint, which is what we'll need for the bus. After cutting the paths between clock domains, the fitter can make the paths as long or as short as it needs to. This can cause skew problems with the bus, such that one bit of a bus can be captured by the clock edge before another bit of the bus arrives for the same clock edge. The setMaxSkew SDC command is a constraint that you will need. The setMaxSkew command targets registers in both clock domains. In this example, setMaxSkew is targeting registers 1 and 2 using source clock and a multiplier to determine the skew value. A good number to use for the skew value is 80% of the source clock period. When using the source clock period option in the setMaxSkews command, you will also need to include the skew value multiplier option as well. 80% of the source clock is a good number to use. Another constraint to use is the set data delay. Since the tools can make the paths between the registers in the first clock domain to the registers in the second clock domain as long or as short as needed, consider placing the set data delay constraint on those paths as an upper bound to make synchronization of the data in the system a known quantity. A good upper bound for the set data delay is 90% of the latch clock. When using the destination clock period option in the set data delay command, you also need to include the value multiplier option as well. In the preceding slides, I talked about the synchronization method regardless of whether it was a single bit or a bus. The multi-cycle path formulation is a way to more safely transfer bus data from one clock domain to another by focusing on mitigating metastability on a single bit and holding the bus data for several clock cycles in the new clock domain before the data are accepted into the new clock domain. Registers in R1 are in clock domain A, and registers in R2 are in clock domain B. Logic in clock domain A is used to generate a data valid signal when the data in clock domain A is ready to be sent to clock domain B, with logic in clock domain B accepting the valid signal and enabling the registers in clock domain B to accept the data. The synchronization between clock domains happens on the valid signal with the synchronizer from clock domain A to clock domain B. This is the same type of synchronizer that I previously discussed, complete with the registers and constraints, so the symbol on this slide is a simplification. You can make this circuitry even more robust by creating an acknowledged signal synchronizing from clock domain B to clock domain A. With this setup, there is one bit that is going through a synchronization process that is the enable line for the bus data. Since the enable line goes through multiple registers and therefore multiple clock cycles before it reaches R2, the bus data will have had multiple clock cycles as it travels from R1 to R2, pushing more of the potential metastability issues on a single bit rather than an entire bus. But you'll still need to put a false path from R1 to R2 through either the setFaultsPath constraint or the setClockGroups command. Once timing is cut from this path, you still need to timing bound this path, and the setDataDelay constraint is perfect for this case in the event you want to put the data enabling logic such as a multiplexer in the path between R1 and R2, as the setDataDelay will go through logics to its destination. Starting with the Intel Quartus 21.3 software, The setFalsePath command does not override the setDataDelay constraint. The constraints shown here look identical to what we had seen before when I created the synchronizer, but in this case, I'll be constraining the bus from register set R1 to register set R2. You will still want to cut the data bus path from timing analysis since it's crossing a clock domain. Set the max skew to 80% of the source clock period, and finally, use the setDataDelay to tell the fitter how much time you want the data to take from R1 to R2. Remember, you have multiple clock cycles for the data bus to reach its destination, so binding the data bus to 90% of the destination clock period should alleviate any potential metastability problems, as this path is a multi-cycle path. Here is the synchronizer circuit that I used in the design. There are two clock inputs, one for each clock domain. The first set of registers labeled Q1 captures the data from the first clock domain. The second set of registers labeled D2 synchronizes the data to the second clock domain, and the third set of registers are there to mitigate metastability. Since the two clock domains are asynchronous to each other, we can tell Timing Analyzer to not consider any crossing points between one clock domain and another. You can right-click in the box of the CDC viewer that represents a clock domain crossing and select the Set False Path option. The Set False Path SCC command tells Timing Analyzer to ignore all paths between clock add 1 and clock add 2. I regenerated the reports after I ran the Set False Path SCC command. The crossing between clock add 1 and clock add 2 is now cut and not analyzed as indicated by the gray box. As I mentioned in the previous slides, I need to consider using the setMaxSkew constraint since this path is a bus, so the setFalsePath command is not ideal in this situation. These three constraints that I previously discussed can be applied through the Constraints pull-down menu in Timing Analyzer as shown in the slide. The setClockGroups SDC command will cut all paths between the clocks entered. The asynchronous switch is set because the clocks in the clock groups are unrelated. The setMaxSkew is set between the two clock domains, and finally, the setDataDelay is applied to the outputs of the first set of registers in the synchronization circuit. Any constraint entered through Timing Analyzer needs to be entered in your main SDC file as well. Regenerate the reports after the constraints have been entered. The CDC viewer will now show the square to be blue, indicating that the paths were cut with the setClockGroups constraint and not colored gray because of the setFalsePath constraint. You will also need to generate reports to show that the max skew and data delay constraints pass timing. This is done by going to the Reports pull-down menu in Timing Analyzer, selecting Other Slack Analyses, and then choosing Report Max Skew and Report Data Delay. You can go through those reports to ensure the constraints pass timing. There is one more path in the synchronizer circuit worth considering. This is the path between the last two sets of registers. These registers are in the same clock domain, and the second set of registers is there to help mitigate any potential metastability issues. We need the tools to place these two sets of registers as close together as possible to further help mitigate metastability issues. When these two sets of registers are placed close together, we get the greatest amount of slack possible, which also means that if the register went metastable, it has the most amount of time possible to settle to a non-metastable value. We don't need a timing constraint between the first and second set of registers in the synchronizer chain, but what we could use is an assignment telling the tools that this is a synchronizer circuit. I showed what the text of the assignment looks like, but we can also apply the assignment through the assignment editor and attach it on the instance. Once saved, the newly attached assignment will show up in the QSF file. This assignment tells the tools to place the synchronizer registers as close together as possible. Now that our SDC commands have been entered into our main SDC file and this new assignment created, rerun the place and route tools since the fitter is timing driven. The outer portion of my design is now constrained to handle the clock domain crossing. Now for the summary. I did a brief overview of what metastability is and how it can affect your designs. I then went over synchronizer circuits and how you can use them to help mitigate metastability issues. I went over the CDC Viewer and Time Analyzer, and how the user interface can help you navigate through the different clock domains that may exist in your design. I then went over a simple circuit to analyze its clock domains in CDC Viewer, and then constraining the design to effectively go from one clock domain to another. Refer to the various resource items listed here if you are interested in learning more about the various topics that I covered in this training. If you require technical support on your Intel FPGA solution, please feel free to make use of the support options shown on this slide. One last thing, when you registered for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you can think of ways in which it can be improved. Thank you.